Welcome to clickmyproject.com.
Now we will see the product for design techniques for decision feedback equalization of multi-gigabit per second serial data link, a state-of-art review. Next we will see the abstract for the product. This study provides a comprehensive review of decision feedback equalization for multi-gigabit per second data links. The state-of-art of decision feedback equalization for a multi-gigabit serial data link reported in that the past decade on compiled and the presented. The imperfections of wire channel, in particular finite bandwidth, reflection and crosstalk and their impact on data transmission are investigated. The fundamentals of both near n-by and far end channel equalization to compact the effect of imperfection of wire channel at high frequency are explored. The detail of examination of the principal configuration operation of the limitation of decision feedback equalization is followed. Design changes encountered in the design of decision feedback equalization for a multi-gigabit data link, including the time constraints, sampling, error propagation, arithmetical operation, highly dispersive channel and power consumption, and techniques and circuit implementation that address challenges of the studied. The need of adaptive decision feedback equalization and the principle of adaptive decision feedback equalization are investigated. Finally, the performance of adaptive decision finite equalization is examined and their proofs and cons are compared. This decision feedback equalization methodology is applied to the adaptive filter architecture in our process. The adaptive filter architecture decision feedback equalization methodology to be followed by this method. Then we will see the flow diagram for the product. The input samples and the error samples to apply the delay unit architectures. The delay unit architecture is mainly based on the register element. The deflip register elements to use the delay adder process. Then the delay element result is applied to the partial border generation unit. The error bit samples is to create the error coefficient manner. Thus, add the addition work to the error input bit samples using the partial border generation architecture. The partial border generation addition architecture is mainly based on the carry select addition process. Then to apply the shift add architecture block. The partial border generation result is to pass the shift add architecture block. The shift add architecture block is used to the addition the partial border generation results in separate manner. This process is mainly used to reduce the carry propagation time and to reduce the hardware complexity for the shift add architecture work. Then the shift add architecture result is applied to the delay and adder element. The delay and adder element mainly used for the store the results in register, then to apply the final output results. The final output results to get the delay and adder element. The delay element is mainly used for the deflip register element. The adder element is mainly focused by the LSB and MSB position for the shift add architecture result and to apply the delay and adder unit elements. The final output samples is mainly based on the synthesis and simulation results elements. The simulation results is mainly passed by the binary results element, and the synthesis report is mainly focused by the satisfy the parameter results for the in our architecture. And finally we see the output for the product. First of all, we open our processing folder, then we open the Xilinx ISC project. Our program is developed in VHDL language. Then we select the waiter update block to select the simulation work, then to select simulate behavioral model. we run the process for our processing result, then open the Xilinx ISM projects. The simulation behavioral model was completed successfully. Then create the ISM project list. Then we apply the binary input and to calculate the output weighted bits. Now apply the 16-bit data length for our project. Then add the error signal in coefficient manner. Then apply the clock pulse. We can create the programmable process. Just we close the simulation process. Next we go into this implementation work. The implementation work to create the view RTL schematic. Just we run the schematic diagram. The RTL schematic diagram is mainly used to create the RTL diagrammatic representation. Just we double click this diagrammatic representation is mainly used to what are the logical blocks is placed in our weighted filter architecture. Then the technology diagram is represents the what are the lookup table and input output buffers, then wire connections and flip-flop pairs to be applied by the our overall weighted filter architecture. Then we go to the design summary result, then the synthesis report. Just we generate the synthesis report for the weighted filter architecture. This architecture results is to calculate the area of the device utilization of weighted filter architecture, and finally we calculate the timing allocations for the latency and delay time calculation for our weighted filter architecture level.